All right? Here's the Ranger. The Ranger travels in a circular path. All right? Our goal today is to use our circular motion stuff with a frame of reference with respect to this. Okay? So, have we talked about any other amusement park rides already? We talked about one other one. What was it? What amusement park ride did we talk about a couple weeks ago? What was it called? Marineland. Oh, the Skyscraper, right? The Skyscraper at Marineland, right? And we talked about what amusement park rides do, right? Like amusement park rides create fun, create entertainment, create anxiety, excitement by changing what? Your apparent weight. Awesome. All right. A synonym for apparent weight was what? As you're sitting in your chair, all right, what dictates your apparent weight or how heavy you feel? The normal force. All right. So amusement park rides create thrill, excitement, anxiety based on how they change the normal force, to change how you feel, what your apparent weight is. So keep that in mind as we go through this process right here. All right, so here we are. We're in the Ranger. None of you people because you're all late. All right, but somebody is in this Ranger. What are the forces acting on somebody sitting in the Ranger? Give me one minute.
Weight going down.
Weight goes down. Always great to get called on first, right? Because you can use that one. All right, and it's a no-brainer. Weight going down. I like it. That's the one I want to pick too. Weight goes down. And Josh.
Force of gravity pushing towards the center, like moving in a circle. So keep it in the circle, wouldn't it be pushing this way too?
Yes and no. To keep this thing in the circle, doesn't there have to be something pushing in towards the center of the circle? 100%. All right? 100%. Is it the force of gravity, though? No. The force of gravity between the Earth and the object is this thing. Right? That's the weight. Is there a force of gravity acting between this person and the center of this thing? Yeah, but it's so minuscule because the mass of this thing is so small relative to the Earth. So in reality, we don't write that thing in our force diagrams. Weight is the force of gravity acting down. What's that force that's acting up towards the middle? The normal force is acting up towards the middle. Like imagine, like you're sitting out here, the people over here are facing this way, and the people over here are facing this way for you, Lamos. They're sitting right here. What are the forces acting on? Well, the chair is pushing up on them, right? So the chair creating a normal force pushing upwards, all right? Now, if you can imagine, right, there's a back to this seat, right? So this thing might be pushing them forwards. So they're I'm gonna say F sub S, force of the seat. In reality, though, we're not even gonna talk about that. Because when we're talking about circular motion, which forces matter? The forces in what plane? The radial plane. And our radius, as Josh says, is up through here, all right? So the sum of our forces acting radially must be mv squared over r. And if I'm going to simplify this force diagram, we're only worried about the normal force going that way and the weight going this way. And we could even say there might be some little debate as to whether this force actually exists, right? Because if the object is already in motion, do we need a force to keep it going? No. But likely, the chair is probably pushing them from the back to the front. Okay? All right. So, Erica, give me an expression for some of the forces acting on a person sitting in here based on this particular diagram. Fn minus W equals mv squared over r. I love it. I love it. Can we switch the Fn and the W? Can we make it W minus Fn? Probably not a good idea because we always want the direction of the acceleration to be positive. And in circular motion, we know that the acceleration is going towards the center of the circle, acts as a centripetal acceleration. So the center of the circle is going to be positive. That makes the normal force positive. and the weight negative. Okay? What are we focused on here? How do amusement park rides create excitement? They change the what? Apparent weight, which is synonymous with what up here? The normal force. So let's trace the normal force as we go through today. The normal force then would equal W plus mv squared over r. Well, this makes total perfect sense. It says a lot, and it makes total perfect sense. When you load the Ranger, you layman's wouldn't know. When you load the Ranger, you load it at the bottom. It would be a really difficult ride if you loaded it while the thing was moving. So the Ranger stops, people get in. If the Ranger is stopped and you get in, then the value of this V is 0. And when you get in, how heavy do you feel? You feel your normal weight. This is true when you just get in there and you sit down. When you just get in there, I'm loading the Ranger. I get in there, I sit down. Normal force pushes up, weight pushes down. The only thing the normal force has to do is counteract the weight. However, once you start moving, if I've got weight down and normal force up, not only does the normal force have to counteract the weight, but it has to keep you in the circle. So your normal force has to get bigger. If you move really, really slowly, then the normal force will equal the weight plus a small number. But if you move really, really fast in the Ranger, the normal force is going to equal the weight plus a bigger number. Either way, how does your weight compare down here at the bottom of the Ranger to what it actually, let me rephrase it. No matter what, how heavy do you feel compared to what your normal weight is when you're down here at the bottom? Carl? You always feel heavier by an amount equal to mv squared over r. So we feel heavier by an amount equal to mv squared over r. And this is basically the same exercise we did when we talked about the elevator. Except it was a linear acceleration in the elevator as opposed to a centripetal acceleration here with the Ranger. Now, what changes when the Ranger moves from there to there? Let's go one more. There we go. So if we focus on this thing right here, what forces, oh, Lily, what forces are acting on the people right here?
Oh, wait,
Yeah, expert. All right. We've got our weight going down. That's the easy one. What else? What other forces are acting on this person here? Erica. Force normal is also going down. That's really difficult. That's really difficult for us to understand. Right? What's the chair look like in the Ranger? It looks like this. Where's the person's head? Down here. Where's their butt? Right here. What direction is the chair pushing their butt? Down. It seems weird because we don't sit on chairs upside down. But when the Ranger is upside down, that's exactly what's happening here. Look at the situation. What's happening when the thing is down here? When the thing is down here, the normal force goes up and the weight goes down. So what do we say? First thing the normal force has to do is counteract the weight. The second thing is to help keep the object in the circle. So therefore, the normal force has to be bigger than the weight by an amount equal to mv squared over r. So you feel heavier. Well, guess what? Does the normal force have to balance out the weight here? No. In fact, the weight is helping the normal force to keep the object in the circle. Which means, how are we going to feel up here? We're going to feel lighter. we feel lighter. Look at our picture. If I come over here and I make our picture, I've got weight going down. I've got the normal force going down. Is the actual weight of the person any different up here than it was down here? No. Super important. Do they feel like they weigh something different? 100%. This thing is traveling in a circle. So we automatically start with sum of the forces radially is equal to mv squared over r. Kyle, give me an expression for the sum of the forces based on this picture.
W plus Fn equals mv squared over r.
Perfect. So if we want to kind of do the same thing here, Fn, we kind of got to do two things with this. We kind of got to do two things. All right? The first thing, God bless you. Oh, get her tested. All right? The first thing is we gotta look at it like this. The second thing, right, is Fn is equal to what? mv squared over r minus w. So we can analyze the expression that we would get for the normal force here, based on what we would get over here. But in some ways, I like to just work with this thing. Okay? And here's why. All right? So let's take a look. Let's take a look. Someone asked earlier, hey, don't we have to put in the seat belt when we're talking about this thing, or the lap belt? Well, the answer to that is no. The seat belt and the lap belt are just kind of like precautions. We don't actually need the seat belt or the lap belt, because if this is done right, all the normal forces here, your weight and your normal force, take care of business, right? So it's relatively easy for me to keep this thing. Everybody's probably done this, right? Like you take a bucket and you twirl it around, right? The only problem here comes with what, Lily? Not necessarily. If I move bridge, I can keep it. Ah! Whoa! What's the issue here? What's going to cause this water to experience some problems? Or more so, really, like I and Lily would experience the problems. Amy, if we go too slow, what happens to the water? It'll follow the ground and get Lily all wet. We're not going to do that, right? But what I will do, I'm an expert, Lily, so I think you're going to be okay. Maybe not, because I can get this thing. Oh, like I'm an expert, so I'm a professional, right? All right, so look at it. The problem comes if you go too slow. If you don't go too slow, or if the amusement park ride does not go too slow, then everything is okay. Amusement park rides are designed to not go too slow, right? So here's another way we can illustrate this. I'm looking for the balls. Where's the wiffle ball? There it is. All right, so look. Basically, hey, the exact same thing we're talking about here is true for this. Except we would just replace the normal force with what force? Tension, right? Like if I stop this right here, what are our forces? Tension going up and weight going down. It's this situation, but I replace the normal force with tension. Right? What about if I stop this thing? Who's up here at the top? The tension is pulling down with the weight. That's this thing, except with tension, right? So I could replace all of this. I could replace all of this with tension, right? So I would say for the rope, the sum of the forces equals mv squared over r, and I get T plus W equals mv squared over r. Now let's look at what happens here. If I take this situation and we focus on the very, very top, right? First off, where would the tension be greatest? At the bottom or at the top? Bottom. Where's your weight the greatest? Let me rephrase that. Where's your apparent weight the greatest? On the Ranger. At the bottom. At the top, it's less. So where's the tension less? where's the tension less? At the top, where's the tension the greatest? At the bottom. Because look at, right now, what's the tension's only job? Keep the ball balanced out the weight, right? As soon as I have this thing in a circle, now it's got two jobs. Two jobs, right? At the bottom, it's got to balance out the weight and keep the object in the circle. So your tension is greater at the bottom than it is at the top. Well, what happens if I slow down? What happens to the string? What happens to the tension in the string? See how the string goes slack, right? I can get to that one speed right up here at the top where that tension goes away, but the ball keeps going in a circle. What happens to the people up here? They feel lighter, right? But if they totally come out of their chair, what would happen to them? Fall to the ground. What would happen to the water if it loses contact with the tray? It would fall to the ground. So look at what we got here. Look what we've got, right? So in this setup, oh, where's my blue marker? I don't know. All right, so look at in this setup, we cannot change the weight of the object, right? We cannot change the mass of the object. We cannot change the radius that this thing is traveling in, or the ball, or the other thing. So what varies here? The tension varies with the velocity, or the normal force varies with the velocity. Can we get rid of W? No. So mv squared over r has to be greater than or equal to W. Or else what happens? The object would fall out of the circle. mv squared over r has to be greater than or equal to W, or the object falls out of the circle. Now, when would that happen? That would happen as you get velocity to be smaller and 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 smaller. So as v goes down, mv squared divided by r approaches W. There's that one minimum speed where mv squared over r equals W. Well, look at it. If mv squared over r equals W, then what's the value of the normal force? 0. If mv squared over r equals W, what's the value of the tension with respect to the string? 0. And if the speed drops below that v, what happens to the object? It falls out of the circle. Now, the Ranger is the exact same thing as a roller coaster. So if you've been on the Viper, let's get rid of that one. Let's go to the Viper. Here we are on the Viper. Here we are. This is the part that always gets me, like it freaks you out. You think you fall, but now you got this little extra thing here. Here we go. Here we go. Here we go. Here we go. Now we are at the bottom of a loop-de-loop. If we are at the bottom of this loop-de-loop, I'm sitting upright. The loop is above me. The normal force goes up this way, and my weight goes down this way. How do I feel compared to my actual weight? How do I feel compared to my actual weight? Heavier. That's this situation. If I got into the Viper and it was stationary, the normal force would have to equal my weight because its only job would be to balance out the weight. But in this particular case, this thing has to balance out the way and keep the cart in the circle. So your normal force has to be greater. You feel heavier at the bottom of a loop-the-loop in a roller coaster. So as we approach this loop-the-loop, if we are under here, that's this situation. Obviously, if you're at the bottom of the loop-the-loop and you wait a couple seconds, you end up upside down at the top of the loop-the-loop. How do you feel if you're upside down at the top of the loop-the-loop? You feel lighter. Because here's your math. Here's your math. What happens if the cart goes too slow at the top of the loop-the-loop? It would fall down. Now, a roller coaster has some safety wheels that would prevent that from happening, right? That would prevent the cart from falling. What do you have to prevent you from falling? You have those shoulder straps. Did my water over there have any shoulder straps? Did it need any shoulder straps? No. In reality, when you're on the Viper, right? Like they wouldn't let you do this, but like if you really wanted to, you could go without that shoulder strap. It's really just for like people's, mentality, right? But as long as the roller coaster is designed appropriately, you don't actually need that thing. If you're going fast enough, you'll always have a normal force here, right? If mv squared is bigger than mv squared over r is bigger than w, the extra has to get accounted for with the normal force. And if your butt is being pressed against the chair, you're not falling down. So you'd actually be okay in this particular situation. You feel lighter at the top of the loop-the-loop than you do at the bottom of the loop-the-loop. Now, where's my Superman? We've got a couple extra people on the Superman. Where's my Superman people? Just one extra? Lauren and Sam? All right. Now, does the Superman have any loop-the-loops? No. But what the Superman has... Oh, there it is. First off, let's back this up a little bit. All right? So first off, does the Superman have any loop-the-loops? No, they don't. But doesn't the Superman fall like that and then kind of balance itself out? 100%. Isn't this a part of a circle? Guess what happens right here? How do you feel right here? You're at the bottom of a loop-the-loop that doesn't actually turn into a loop-the-loop. How do you feel right here? You feel heavier right here because it's essentially this situation without it being a loop-the-loop. So when we talk about circles, it doesn't have to be a full circle. In fact, the physics of these loops mandates that they are not actual circles. We're not going to get into that, all right? But there's a physics reason why they're actually teardrop shape and not circles. Any portion of a circle, we can use the same exact mechanics with. Now, not only is it portions of a circle, but look at that. Isn't this a portion of a circle? Like, it doesn't have to be loop-the-loops. You can have the same feeling of feeling heavier if the curve is a horizontal curve. Anytime you are in a roller coaster and you make a turn, or any amusement park ride, all the turn is doing is messing with how heavy you feel. And that's how these things get designed, right? And that's why there's thrill or anxiety. What do we got here? We're at the bottom of a hill that becomes not a hill. We're back in a situation where it's partially a curve. And we're getting to the part where we really want to talk about it. Well, this is obvious, right? There's a circle. We got the same mechanics here. Obviously, the situation is a little bit different. It's sideways, but we could do the mechanics there. Still in a circle, still in a circle, still in a circle, still in a circle. Oh, here we go. You think the ride is over. You think the ride is over. You're coasting into the end. You're coasting into the end. And at the very end, they got these tiny little loops. These always get me because I think I'm done with all the heavy stuff. But in reality, we've got some physics to talk about here as well. You don't like them? Here I am. I'm right here on the Superman. What forces are acting on me? Lily. Weight goes down. What other force acts on me? Lauren.
Force will go up.
With normal forces going up. The forces acting on me right here are weight going down, normal force going up. What's that look like on the board? Where else do we see that on the board? Yeah, that's over here. So we got this situation here at the bottom of a loop. If I had to draw a picture of like what's going on here, right? What's going on over here? This is the top of this loop right here. Why is this different from this? Now it's obviously different from this because we're not upside down. Why is this different than this? I'm right side up over here. I'm right side up over here. Hey, we're outside the circle. If I want to kind of keep on doing what I'm doing here, I'm up here. If I'm drawing this picture, I'm up here. How's that change things? I got W here. I got the normal force up here. Isn't this part of a circle? So as long as I've got this as part of a circle, and my mechanics say sum of the forces radially is mv squared over r. Sam P, give me an expression for the sum of the forces acting on this object based on this picture. Love it. That's an awesome answer. Why did you do weight minus the normal force? They're in opposite directions. But wait a minute. They're in opposite directions over here, and we did normal force minus weight. Who can tell me why it's appropriate over here to do weight minus the normal force compared to over here, the normal force minus the weight? Read.
Because weight is the centrifugal force causing the acceleration.
Kind of. I got a little hesitancy with those words. Those words were weight is the centripetal force causing the acceleration, or something along those lines. Remember, centripetal force is the combination of all radial forces. So in reality here, the centripetal force is the combination of these things. But over here, it's also the combination of these things. Now the combination is a little bit different over here, right? But one of these two forces is not the centripetal force, while the other one is not. In reality, the centripetal force is the net combination of all forces acting radial. You're kind of correct. Who's got a different way to say? Josh wants to show his buddy up.
It's because weight's going into the circle on this diagram and force going out of it as opposed to the other side.
In the direction of the acceleration, we always want to put as positive, right? So therefore, this becomes positive and that becomes negative. Well, then what's the normal force equal to? W minus mv squared over r equals Fn. So in reality, hey, I've got one sentence, two sentences, three sentences that we've got to familiarize ourselves with. In reality, I don't want you to familiarize yourself with that. I want you to be able to duplicate that based on the physics, but there's three situations. How do we feel up here compared to our actual weight?
go up there.
Look at the map, look at the situation. Kyle, what do you think? Carl, rather.
You feel a lot lighter.
You feel lighter. How come you said that? It's a couple different explanations.
Because the normal force, or it's gonna be your weight minus the mv squared over r, so it's always gonna be less. Actually,
What's the car stationary right here? What's mv squared over r equal? How heavy do you feel? Your actual weight. As soon as that car moves over there, you feel lighter by an amount equal to mv squared over r. So you feel lighter by mv squared over r, or by an amount equal to mv squared over r. Okay, that presents some problems here. First off, I always associate with this. Am I getting your head here? Nope, that's not good, Richard. This I always associate with Gunville and Worley. Now, there's lots of different intersections where this takes place. But the next time you go over that intersection at Gunville and Worley, you'll notice there's a little hill in there. You come down from Genesee Street and you're going down that overpass. I always get a bit of steam going. I'm going fast. Woo! It's almost like you get a little bit of air. You feel lighter at that intersection and lots of intersections. And this is the reason why. Now, anybody know what happened at this spot on the Superman?
Wasn't there someone who
My
fell out?
parents were on the ride when it happened.
Get out of here.
No, that's the
Which time? It happened twice. So the answer is, didn't somebody fall out? Yeah. Actually, it happened twice.
with
People fell out and died.
Didn't have legs or
So
whatever.
one person didn't have legs. One person was super heavy. And they flew out. Now, why did they fly out? Right? Well, look at the map. Look at the map. If you're stationary, the normal force is equal to W. As you go faster and faster and faster and faster, what happens to mv squared over r? It gets bigger and bigger and bigger and bigger and bigger and bigger, till eventually, if mv squared over r equals w, what's the value of the normal force? Physically, what would happen to you in your chair or the person on the Superman if their normal force was 0? While you might fall straight down if the chair was removed from you, you're elevated off the chair. You're not touching the chair. You're out of your chair. Like when I said you feel like you're getting some air on that intersection, that's exactly what happens. If you get going too fast, your normal force is equal to 0. The faster and faster and faster you go, you might get projected off of that chair. What's usually there to protect you in the Superman? Yeah, lap bar in the Superman. In that particular case, the lap bar does do something. The problem is, the person that had no legs, it couldn't hold. And the person that was too heavy never closed the thing enough to make sure that it held you. So I think 2 people died. I know the person with no legs passed away, and I'm almost positive the other person did. How come? Well, because the thing was going too fast, which created a situation where the normal force was 0 or negative, you could kind of say. Basically, what's the significance of that? You're off of your chair. And in this particular case, you're off of your chair and you're flying away. All right. Now that's vertical circles. We've used the same principle.